Hello, my name is Fred Carlo. I'm excited to share my understanding of conditional probability and Bayes' theorem. I'll first give you a short overview on its history and explain this concept with examples and end it with an application.
It all started with Thomas Bayes with his groundbreaking work in Bayes' theorem.
Unfortunately, before he could share his insights with the world, he passes away in the year 1761. His friend Richard Price finds Bayes' work and understands the importance of it, and then publishes his work in the year 1763. It takes a lot of time for the world to notice it, but our friend Pierre Simon Laplace takes a look at Bayes' theorem and kind of gives it a French twist, and publishes his work in the year 1812 to what we today know it as conditional probability. What is conditional probability? Imagine you're on a date with your girlfriend, and out of the blue she asks something that's not even in the menu. She wants a carrot cake. You know when something's not in the menu, they're probably not going to give it. But for the fact that your friend is the chef of that restaurant, so there is a probability that you could get on a favor. So you probably say yes and save the date. This is what essentially is conditional probability. Conditional probability is finding out the probability of an event given that you have some other piece of information which can influence that situation. So now let's see the mathematical explanation of it. So mathematically, probability of A given B is calculated as probability that A and B occur divided by the probability of B. Now let's look at this with an example. Mr. Smith has two children. At least one of them is a girl. What is the probability that both are girls? What we are given is that one of them is a girl. But what is the probability that both are girls? The different possibilities are that both could be girls. One could be a girl and a boy. It could be a boy and a girl, or it could be both boys as well. So let's use conditional probability here. So probability of both girls given at least one girl is equal to this format. Probability of both girls and at least one girl divided by probability at least one girl. Let's calculate them. What's the probability of both girls and at least one is a girl? There's only one possibility that both are girls, and I'm making them select only one is a girl. So that's going to be one out of four scenarios. What is the probability that at least one is a girl of the possible four scenarios? There's three places where this could happen, so it's 3 out of 4. You substitute this into the equation, you get 33%. So this is how you solve based on conditional probability. Now let's look at Bayes' theorem. From conditional probability, we know that probability of A given B is given in this format. What if it's the other way around? Probability of B given A. We get the same thing, but we find that the intersection of these two are probably the same. You see from the Venn diagram, you see that whatever be the probability on both sides, the intersection is probably going to be the same. So we can write the second equation in this format. And now if we substitute this equation into the first equation, we get that probability of A given B is equal to probability of B given A, it's probability of A divided by probability of B. And this is Bayes' theorem. The reason why Bayes' theorem is useful is sometimes computing the probability of A given B is easy, and sometimes computing the probability of B given A is easy. But in any scenario when one of these two is easy to compute, you can get the other probability using this relation. This would save a lot of time in collecting unnecessary data to compute the other probability. Now let's look at the previous example, but in the context of Bayes' theorem. Now let's solve the previous example with Bayes' theorem. We know that at least one of them is a girl, but what is the probability that both are girls? Now, in Bayes' theorem, we could write this problem statement in this format. Let's calculate them one by one. Probability of at least one of them is a girl, given both are girls. Now, given both are girls, that's just one scenario that both are girls. So probability of at least one being a girl is 1. It's 100%, so just 1. What's the probability of both girls? Out of these 4 scenarios, there's only one probability that's going to be a girl. Both are girls, so that's 1 out of 4. The probability that at least one girl, you can see there are 3 possibilities of that happening. So it's 3 out of 4. You plug it into the Bayes' theorem, you get 33%. So it's the same as the previous one. So we can say that Bayes' theorem validates conditional probability. Conditional probability in the Bayes' theorem have several applications, and one among them is sports betting. betting companies need to set odds for various scenarios of a match, like a team winning or not, or a player scoring or not. If you say it's 55 to 1, that means if you put your £1 in and you win that bet, you're probably going to get £55 off of that bet. So it becomes very important to set very careful odds on different scenarios. Let's say, for example, if they want to set an odd for Mo Salah scoring in the next game being Arsenal, which is a big game, and they already know that Salah has scored his last 4 matches. So this increases the likelihood of that him scoring again. So they probably should set a lower prize money on that bet. So betting companies use many such information available in order to predict a player's performance. Hence, they use conditional probability, understand if a player is going to score or not, and accordingly, they change their odds. This way, conditional probability and base theorem plays a major role in the sports betting business. These are the references that I've used to build my slides. Thank you for taking the time to review my video. I hope you have a good Christmas and a wonderful New Year. Thank you.